Perfect. Hey, so this tutorial I'm gonna show you how to do rain simulations or runoff simulation. And uh, I have also provided it on Canvas and their modules, so you're gonna be able to find it um, in under tools. Let's see here. Runoff and slope, same grasshopper. I will upload one with today's date, which is on the 18th. So when you're going to do your simulation, I would recommend using that one. Yeah. So essentially, the simulation requires you to have Rhino 8. It doesn't require you to have any plugins because I've coded it myself, and so it doesn't use any plugins. You might have to download something, but it happens automatically when you open Grasshopper, as long as you have the internet connection. I believe it's essentially pufferfish and maybe something more. But nothing that you need to download from Food for Rhino or similarly. So to make this simulation, right, the first thing we want to make sure that we have is a good surface. And we want to make sure that the surface is not trimmed or damaged in any ways. Like for instance a surface with a hole or a surface that's irregular or similar. To ensure that we have that, we always want to do a drape on whatever surface we're using. And of course drape also works on multiple objects, no matter if it's mesh, polysurface, a surface, or sub-D or something else. And as you can see here, we end up with a surface that is mimicking both the all of the different objects. So once we have a surface, we can head into Grasshopper, and Grasshopper is right, well, never mind. Let's do show. Show. Alright, so first thing we need to do, just clear the values here, is to of course set the initial one. So this is where we get the input. So we're gonna set one surface, and we should now see yeah, the runoff simulation starting. I'm going to hide this surface inside a Rhino so that I don't get to see it. And essentially, we have a couple of different inputs that we need to take into consideration. The first input is how many simulation cycles. I'm going to put it on 8,000, and you're probably not going to need any more than that. It's a pretty large number, but lowering it can reduce the amount of time the simulation takes, but it's usually not worth it because simulation count is relatively low effort. Raindrop count, however, is what I would adjust to make the script faster. So, for instance, having lower raindrop counts, or for instance, having 8 higher number for a more exact simulation. Something to have in mind though is um, first up, this does not affect how much rain there is. The calculation is using the entire area's surface area and divides it by how many raindrops you have. So it doesn't matter how many raindrops you have, it really just makes it more precise to have more. But it will take a lot more time, so beware of that. The second thing here is how much rainwater we're using. 80 millimeters, that's quite a lot. That's 10 millimeters more than what you would see in 100-year rain. Um, and um, and this 100-year rain is something that I'm estimating by um, using data from SMPOE. You can use other data sets if you have any that you think are more reliable. And you can find this link here. And this is just some estimations that I'm basically making when I'm doing some of these calculations and when I'm thinking about rainwater. And here you can see the different data sets that I was using when both where you can download the data sets and the data set itself. The way you basically calculate what is a 100-year rain, it's the likelihood of this type of rain happening within that year. And if that likelihood is 1%, then it's a 100-year rain. If it's 2%, it's a 50-year rain. And I would essentially say that these type of rains are probably going to be more common in the future, but we're using a combination of predictions and historical data to estimate these type of things. The second thing here is pond grouping tolerance. The pond grouping tolerance, this defines if you want to see every single raindrop and how much rain there is, well, there, or if you want the raindrops to, let's say, group up in some ways to become, let's say, a bigger pond, so you don't need to see as many variables, or if you want most of them to group up. And it's just a way for us to try to, well, make slightly better estimations around the simulations and whatnot. And at the end of the day, this of course not reality, but it's a simulation. It's something where we're trying to get some data on certain outcomes. And then we have this next part here, which is the output part. Here we see some valuable data. For instance, the runoff simulation here. And of course, we can turn things on, turn them off if we want to. The ponds, they are basically both a representation of how much water is in each pond. We can see that they are in fact 3D objects that are supposed to be in the right size in relation to how much water there is there or is gathered. And we of course also have the tags that show the amount of water. Same with the amount of collected water here. the list goes from the smallest to the biggest pond. And so the number really is just expressing an index. You might also see that the rain comes in, raindrops comes in values of 600, and that's because the total amount of rain has to do with how big of an area we are working with, and since the area is divided by the amount of raindrops, we get this. What we're also going to see though is there's a couple of patches here without any rain. The reason why that's the case is because, as we can see here in the rain endpoints, there's some points that didn't make it into the simulation, and these are points that happen to land on entirely flat areas where no more water would run. That basically excludes them from the simulation, and we can also see that it doesn't actually show up in collected water per pond, but it rather is in its own category of amount of rain on a totally flat ground here. The second thing we can look at here is if you want to see exactly where the rain simulation starting points were. And in this case, it's only showing the ones where that actually made it into the simulation. So this is essentially everything about the water simulation. I'm not going to go through everything, but I can say essentially how it works is the surface turns into a mesh. So in theory, you could also use a mesh, but I would still recommend just draping the surface over an area and then letting this convert it into a mesh itself. It will then project random points onto this mesh, then do the simulation over here, which we see is the heavy one. And then it will do some calculations, group the ponds, and later on do some labeling, and eventually that's how we get the results. The second thing I'm going to show you is the slope script. The slope script is relatively easy as well, and we can set one surface and activate it. So now I see that we have both simulation up and running, and all I see is that some areas are flagged as green or yellow, whereas most of it is white. And I'm going to shut down this simulation for a little bit, and the reason why this is it is because it will show you different colors depending on the flatness of the ground. So if we look in 3D view here, we can see that the flattest areas they will be light green, then followed by yellow areas, and then more kind of orange looking, and finally red. I might still continue slightly adjusting some of these color schemes to make it even more readable. And in theory, you can do that yourself by going into this component. Yeah. So the color scheme here might not be entirely correct, but essentially it's gray, orange, yellow, dark green. So these parts are entirely flat, more or less. These parts are very gently sloping. And then we get to these yellow parts that are kind of darkish yellow, that are around 5 to 8% slope, and then these kind of dark. Now that I look at it, it looks almost deep green, but I might slightly adjust this so it's more redder, maybe. Yeah. Um, Maybe something like that. Yeah. Yeah, that's more orange. And that will basically be the end of what's walkable. And using this, you can get a bit of an understanding of the slopiness of your area, but also what places might become good paths, or where you have created paths. Or you can also estimate how fast the water will run in some of these areas too. Um, and in this case, we actually have some of these parts turned on as well, but I would maybe be careful with that, since sometimes they can be quite heavy. Like for instance, this part that shows you exactly how many, what each part have as a sloping number. Um, and as always, you can turn things off and whatnot if you're not gonna use it or you don't need it. Let me turn these parts off. Um, maybe just have this one on. Something like that. Of course, you can also change the contour if you need that. So this is the essentials of how to do this type of runoff simulation and slope simulation. We're going to have some more tutorials later, so I'll send a message about that. And I think it's good to try to use this if you're working with some type of landscape architecture. It can give you a lot of information about how you might want to design to slow down the water, to gather the water, to basically just give you some data on how to design. And at the end of the day, it's not about necessarily needing to do all of the simulations, but it really comes down to really trying to figure out how can these simulations become great arguments for the designs, for the concepts that you want to accomplish, and letting them really guide you both in your design process, but also as communication tools for other people who might not know the same type of things regarding, let's say, how water would flow on a certain area. It can also be a great way of just visualizing data in general. I hope you find it useful. I'll see you soon.